Okay, so this is Unit 11, Video 1, Part 2. And so we're going to talk about something called Coulomb's Law. This is named after a guy named Charles Coulomb. You'll read about him in your book when we go through it, but I didn't think it was necessary to put it in the video. So Coulomb shows that an electric force has the following properties. So in short, the force will be along the line joining the two particles. So it would be the shortest space between them, basically. It's inversely proportional to the square of the distance between them. It's proportional to the product of the magnitudes of the charges. So basically Q1, absolute value of Q1 times absolute value of Q2. And it's attractive if the charges are of opposite signs and repulsive if the charges have the same signs. Basically, that was just reading you out loud the equation, which I'm going to give you in a second. So just hold on for it. And there it is. So mathematically, the force between any two charges is going to follow this equation. R is the distance between the two charges. You want to make sure you have the absolute value of the charges when you plug into the equation. And K is called Coulomb's constant. So you can see the unit. That's the thing I want you to take note of. Newtons, meters, and coulombs. So you cannot be in any other units when you use this constant. I would shorten this to 8.99 times 10 to the 9. It's just a lot easier when you plug it in your calculator. That's kind of a lot of decimals. So typical charges are in the microcoulomb range or maybe nanocoulomb range, and I'll show you how to convert those a little bit later. But make sure you use coulombs in the equation, so you have to convert those. Remember that force is a vector quantity. That's going to come up a lot. You're going to need to remember how to add vectors. And it applies only to point charges and spherical distributions of charges. So you're only going to see round point charges or spherical charges. And then R is the distance between the two centers of the charge. That will be pretty clear in the problems what R is. Okay, this is just a table showing you the charges of our standard electrons and protons. So electrons have a charge of negative 1.6 times 10 to the negative 19 coulombs. Protons are positive 1.6 times 10 to the negative 19 coulombs. And then over here you can see their masses, which you will not come about in the first homework, but it may be good to know. So that table is in your book, so just make sure that you know it's there. And obviously a neutron, since it's neutral, is going to have no charge. Okay, so here's the simplest of the electric forces. So here's charge 1, it's positive. Here's charge 2, it's positive, which means they're going to repel each other in exactly opposite directions. So the force on Q2 is going to go this way, that's showing you. The force on Q1 is going to go that way. If you look at this notation, it's F12 for charge 2. So this means that the force on object 2 from 1 is going to be whatever. So that's how you notate it. Sorry about that. That's how you notate this. The force from object 1 on object 2. And then you can see it's the exact opposite for charge 1. And they're going to be in separate directions. They're going to be equal in magnitude, but in opposite directions. So basically F12 equals negative F21. And then you can see the distance between them is R. Here's the same diagram, except for now you have a positive Q1 and a negative Q2. So their forces are going to be toward each other, but same notation, same thing with the distances still are. You still find it the same way. You'll just now the direction's different. You don't need to write everything down in this slide or the next, but just wanted to connect the two. Electric forces are the second example of field forces that we've seen. Remember, gravity was our first field force. And then remember, the other types of forces are contact forces. The bell just rang, sorry about that. And so they're actually really, really similar. If you remember, let's go to the next slide. I'm going to show you something. So if you look at the new force we have, it's F equals K Q1 Q2 over R squared. If you remember the gravitational force, it was G M1 M2 over R squared. So they're really, really similar, and that's just what these slides kind of talk about. You can read further into it in your book. It doesn't help us that much to know this, but it's just kind of cool that the two field forces have very, very, very similar equations. Okay, so the superposition principle in this chapter, it sounds more complicated than it is. Really, all this means is that if you have one charge, say right here, and you have two other charges, say this one and let's say this one, if we're looking to find what's happening on this charge, it's gonna have two forces. Let's say that this one's positive, this one's negative, and this one's also positive. So this, let's say 1, 2, and 3. So we're looking at 2. Charge 1 is going to repel charge 2 and push it this way. Charge 3, since it's negative, is going to attract charge 2 and bring it this way. So all that this slide is really talking about is that if you have those two forces, those are vectors, and you need to add them like vectors to find the net force on charge 2. That's it. And we're going to practice this. So this is exactly what I just said. So I don't know what's with the question marks, but you can ignore those. So the force exerted by Q1 on Q3, so here's Q3, here's Q1, here's Q2. The force exerted by Q1 on Q3, since they're both positive, is going to be a repulsion force, so it's going to push it this way, so you can see that blue arrow. And then the force exerted by Q2 on Q3 is going to be attractive because Q2 is negative and Q3 is positive, so it's going to push to the left. The total force on Q3 is the vector sum of those two forces. And so we're going to have to look at those two vectors. You have one this way and you have one this way. And we're going to have to add them. I would suggest you add by component. I think that's the only way. And I'll refresh your memory on how to do that. Okay, so I'm going to pause for just a quick note. In this chapter, you're going to be using coulombs as your unit for electric charge. So a lot of times, though, in the problems, they're going to give you microcoulombs or nanocoulombs. And you can kind of see what it looks like there. So I just want to show you how to convert. So if you guys want to take a second to write the conversion down, microcoulombs is 1 × 10⁶ microcoulombs per coulomb. So basically, if you had, let's say they gave you 5 microcoulombs, that would be the same as 5 × 10⁻⁶ coulombs. That's all. For nanocoulombs, it's just 9. So if they gave you 5 nanocoulombs, that would be the same as 5 × 10⁻⁹ coulombs. So you just need to remember that micro is 6, nano is 9, and it's going to go like to the -6 or to the -9. Okay, so here's another quick concept check. So pause your video now and answer the following question in your notes. I'll tell you the answer when you're done. Okay, so object A has a charge of +2 microcoulombs. Object B has a charge of +6 microcoulombs. Which statement is true? Hopefully you said B. The force of A on B is equal to the negative of the force of B on A. The ratio between what charges they have does not come into play for the forces. They are going to exert equal forces. And this goes back to that law in chapter 4 and Newton's third law, where every force has an equal and opposite reaction. And so that's what's happening, is object A is pulling on B with some force, so object B is going to pull on object A with the exact opposite force, but the same number. Okay, for this example, it's going to take me a little bit of time to write it down, so I'm going to go ahead and have you guys just write down the example, draw the picture, and write the question, and then we're going to go ahead and go over this in class at the very beginning of class on Monday. So just write down the example, draw the picture, and then we will go through it together on Monday so that you guys can practice your vector addition.